Piecewise functions are functions whose ARC, or average rate of change, only stays constant for different intervals of the input value. So we piece together portions of different linear functions. So what we're going to do is we're only going to see in this particular chapter pieces where every piece is a line. So that makes things kind of easy because we know we'll have a slope and an intercept. So we're going to look at the following scenario and see if we can generate the piecewise function that plays into this. So it says Christy, Tim, and Dory are taking a road trip to see their favorite band, family, and friends. They leave Athens at noon and drive for 4 hours at 60 miles per hour. They stop for lunch for an hour, get back on the road, and drive 50 miles per hour for 2 more hours. And when they hit down, there's a traffic jam, so they only go 20 miles an hour for the remaining half hour. Sketch a function of distance versus time for their journey. So what we want to do here is we know we only need to draw the first quadrant because we're not going to have any negative times. And so when they start their journey at time 0 in Athens, right, they've traveled 0 miles. So this is going to be the distance we've gone in miles, and this is going to be the time, right, in hours we've traveled. So this is going to be miles. So let's just look at this one piece at a time. So the first thing is they leave Athens at noon and drive for 4 hours. So I'm going to put a 4 on the x-axis. And they drive for 4 hours at 60 miles per hour. So if we go 60 miles an hour for 4 hours, we've traveled a total of 240 miles. So up here at 4, we've gone 240 miles. So when we connect these two pieces, and we can see here, right, that our slope of this line is going to be 60, right? So 240 over 4 across. So remember, the speeds, or the rate of change, is our slope. Then in the next leg of our journey, right, we're told that they stop for lunch for an hour. So if they stop for lunch for an hour, it's now 5 hours after they left, and they haven't gone anywhere. So this is just going to look like this, right? It's a horizontal line. They're still 240 miles from home, and we can see this line, right, has a slope of 0. They haven't gone anywhere. Then it says they get back on the road and drive 50 miles an hour for 2 more hours. So now 2 hours later, it's 7 o'clock, and they've driven 50 miles an hour for 2 hours, so they've gone 100 miles. So I'm going to put this up here. So now they're 340 miles from home, because we just add 100, right? And now when I connect these two dots, right, we see that the slope here is 50. And then when they get to town, there's a traffic jam, so they go 20 miles an hour for a half hour. So if they'd gone 20 miles an hour for a full hour, right, we would be at 20 miles, but they only did it for 30 minutes. So that means they've only gone 10 miles. So let's see here. I'm going to try to pick a good color for us. So we only go a half hour, so that's 7.5 hours from home, and they've only gone 10 more miles. So that means, right, they're a total of 350 miles from home. So this is the graph of what this would look like. Oh, and sorry, 10 was the distance. They were going 20 miles an hour, so the slope is 20, not 10. And I'm going to write that a little clearer for y'all. There we go. So this slope is 20. So the rate of change is the slope. So now we can see, right, that this is what happened. This is our sketch, right? So now we want to come up with a formula for this. So the way a piecewise function works is we find the equation of the line, right? This line would actually do this if we let it continue. And then we crop it only to the portion that we want. So the first leg of our journey, the slope of our line was 60, and we can actually see the y-intercept here. The y-intercept is at 0, and this is only true from t equals 0, greater than or equal to 0, to greater than or equal to 4. So the equation of this line is going to be 60t plus 0, or just 60t. The second line has a slope of 0, and we can see that its intercept is 240. So if I were to extend this line out, right, we can see it's just going to cross at 240. So B is 240, and this line is only used from 4 to 5. It was only true for an hour. So this is something we want to keep in mind. 4 cannot belong to both pieces. So if we used it in the first line and put an equal to here, then we cannot put an equal to here. However, an alternative right answer was you could have said, well, this is just less than 4, but then that means we would include 4 here. So the values in these domains can only be used for one piece of the function. So now if I write the equation of this line, it's just 0t, right, plus 240, which is just the constant function 240. The third piece is a little bit trickier. So our line, right, is going to be of the form y equals at plus b. We know a, right, that's 50. So I'm going to plug 50 in. And I don't know what b is, because if I were to extend this line down, I don't know exactly where it crosses over here. However, I can identify points on the line. So the easiest thing to do is grab one of the endpoints. So I'm just going to grab this guy. So I know that when t is 5, this line starts at 240. So the y value is 240 when the t value is 5, and now we can solve for b. So 240, right, minus 250 gives us -10 equals b. So now this line is y equals 50t minus 10. And this is true from 5 to 7. So once again, I used 5 in the second piece of the function, so I don't keep it in the third piece of the function. I just say it starts at 5, and then we let it end at 7. So the fourth piece, we're going to use the same method. Oops, choose the right color here. So we know that our line is going to have the form AT plus B. We know A is 20, so I'm going to grab a point on this line. So I'm just going to grab this guy. So when T is 7, we're at 340 miles. So 340 when T is 7. And so 340 minus 140 gives me 200 equals B. So this line is y equals 20t plus 200, and this is good from 7 to 7.5. So once again, I included 7, so I don't include 7 down here. So now that we found all of these pieces, now we can write the equation in its proper form. So d of t, when we have a piecewise function, we use one curly bracket, and it's two columns. The first column are the equations, and the second column is the domain that goes with that equation. So our first function was 60t, and that was good from 0 to 4. Our second equation was just the horizontal line to 40, and that was from 4 to 5. Our third line was 50t minus 10, and that was from 5 to 7. And our fourth line was 20t plus 200, and that was from 7 to 7.5. So now if I want to evaluate a value at this function, if I say, well, where were they when they had been on the road for 3 hours? I would look at the domain column, I would find the interval that includes 3, right, which is here, and then I would plug 3 into the corresponding function. So I find that when you're building these, colors help, so you can kind of keep track of what we did in each piece of this. So the question is, what time did they arrive? So if they left at noon and it took them 7.5 hours to get there, so t equals 0 was noon, so then that means that t equals 7.5 is 7:30 p.m. How far was their total drive? Well, we can actually look at our y-scale here and see that we got there 350 miles later. So they went 350 miles. And how far had they traveled by 5:30? So at 5:30 p.m., t would be 5.5. So we're going to go to our function, and we're going to find the interval with 5.5, and we can see it's right here. So that means I plug 5.5 into this function. So 50 times 5.5 minus 10 is 265 miles.